could have had all that recorded too.
Thank you, bud.
Yeah. Well, thanks, Mr. Gonzalez. You can message him on Facebook.
Yeah, give him a hug.
I'm going to check later and make sure he puts that tattoo on. So I have mine. So this is mine from the other day. It takes like 6 days for those things to finally wear off. It was Donatello. My wife had to help me apply it because I kept trying to put it on upside down because they're backwards, you know, on the sticker sheet thing. All right, so let's finish our, I think we were just at the very end, right, where we had to make our 2 recursive calls. Everything before the final location of our pivot, and then everything after our final location to our pivot. And then I think the magic should just kind of happen, right?
Oh, and we noted that we have to do the reverse still, I think. We never actually did the reverse in class.
Oh, yeah, that's going to take 5 minutes.
Yeah.
Okay. That's that comment. Oh, yeah.
I'll remove it because that's what it was.
Okay. Yep, no problem. That'll take like 8 minutes.
Yeah.
So it's a little bit longer. Okay, so here's our, I say potentially 2 recursive calls because we don't want to waste a recursive call if we have nothing before. So if pivot is less than, well, so effectively what are we doing up here? Let me minimize this so we have a little bit more code space. So effectively what are we doing up here? We are positioning pivot, right? So when all this code is said and done, we have a counter pivot that should be where the final location of our pivot was. And remember, we started off with pivot being the very last bucket. Remember 2 classes ago, I referenced that, hey, you know, last bucket is sometimes the choice for pivot. What do you think about that? And he shot it down like it was stupid, right? So then we did the insertion sort thing, and then we kind of stumbled upon the idea that, oh, you know, that last bucket makes a little bit of sense because what we can do is we can effectively bubble that guy as far forward as we can and then only have to deal with the stuff before him, right? Because we know everything to the right of him is going to be greater than he is. So ultimately what this code here does is it's going to go through, this is the code that bubbles pivot towards the front, right? All right, so after this code is done, we know that everything to the right of pivot is larger than it. We know the element directly to the left of pivot is less than or equal to it. That just happened to be our stopping place. That was the thing that broke the loop that said we no longer need to do a swap. Okay, so we know the guy right to the left, immediately to the left of pivot must be less than or equal to pivot. So we can actually skip that guy. And then we can just deal with everything from bucket low, actually. I tested her last time and she corrected me, right? Yeah, if I remember correctly, yeah. It was a complete test, not a mistake I would usually make. I did it on purpose. So we start at bucket low and we go all the way up to including pivot -2 or inclusive or pivot -1 non-inclusive. All right, so that's what this loop is doing. So this loop is checking everything to the left of pivot and saying, do I need to throw any of this stuff after pivot? Now keep in mind that the stuff that's after pivot is not sorted at all. Okay, it's just, all we know is it's greater than pivot. All right, so this guy goes through for each one of these guys between bucket low and bucket pivot -1 non-inclusive. So this is up to and including pivot -2. We're going to ask the question, is the current dude we're looking at, should he come after the current pivot? That's what that asks, right? If it's greater than 0, that means the dude that's currently to the left of pivot actually should be to the right of pivot. So we'll do our little swap thing. So we'll preserve the current dude that we're getting rid of. Then we'll shift everything down. Then we'll replace the current position where pivot used to be, even though we just shifted it down 1 to clear up a spot for this new dude. And then we'll go ahead and throw the new dude in that position. We preserved him right there. And then we'll decrement pivot, because pivot did in fact shift down 1. So after this code is done, what do we know? We know that everything to the left of pivot is less than, or let's just write the thing, less than or equal to it. and everything to the right of is greater than it. So now we make the necessary recursive calls to sort the rest of the list. All right, so we have two calls to make. We have calls for everything that's before pivot, and we have calls for everything that's after pivot. Under what circumstance would we not make the call for things to the left of pivot? What would have to happen for us to say that calling this guy, quicksort for things left of pivot is not necessary? What has to be true?
It's a one list.
Okay, how do we know it's a one list?
Can't we just do like a length, or check the length of what's before it, or check the index of the pivot even?
Well, we would check the index of the pivot relative to low, right?
Yeah.
Okay. So I decided not to trick you this time. I say that trick was for last time, the low to zero thing, but yeah. So we're looking at the current position of pivot, where that guy finally lived, because that's his final resting place, right? And we're looking at where is he in proximity to low. We know that he's going to be greater than or equal to low. No, there's no chance that he's over here. Okay, so he's either going to pivot's either here, and this is low, okay, or he's somewhere to the rest to the right of it. Now, if he's at low, we don't need to call it, right? There is no left-hand side. If he's one greater than low, we also don't need to call it, because now it's the one list. I mean, we can do the call, you know, wave our hands and all that stuff, but it's a waste of time. Okay, so really, we only are going to make that recursive call if pivot minus low is greater than or equal to 2, or greater than 1. However you want to write it. So if pivot minus low is greater than 1, that means we have something that's bigger than a one list. If pivot and low are the same, if they're both bucket 3, 3 minus 3 is 0, that's a 0 list because there is nothing over there, that's not going to pass. If pivot is bucket 4 and low is bucket 3, 4 minus 3 is 1, 1's not greater than 1 because that's only a one list, so this would have to be a 2 list or larger. So if this is the case, then we're going to make our recursive call on our left. So we will call qsort here, passing it low and high. So we'll call, what language am I on? I'm in Java. This dot qsort, and I need to pass it a low and high. So low will be the current low, and what will the new high be for this one? This is the call set for everything to the left. It's Josh's Valentine. Just walk by. So what's my high? Go ahead. Pivot minus 1. Everything to the left of pivot. So pivot minus, whatever, 1. I can't decide if I want spaces in there or not. I really want a tennis ball in there, but we already proved that we can't do that. All right, so only under this condition are we actually going to make that left recursive call. Otherwise, it's a waste of time. Okay, and keep in mind that this also prevents us from having to do some extra checking up here to make sure that we're not, checking things that aren't part of the current list and that kind of stuff. Because we know that we only are calling quicksort if there's a list to sort. All right, so that's whether we do our left call. Now, under what circumstances do we do our right call? Kind of the inverse of this guy, right? So if high minus pivot is greater than 1, if that's a true statement, if we have something larger than a one list to the right, okay, then we'll say this dot qsort, and low, what's the value of low going to be? Pivot plus 1. Oh, come on. and then high is going to remain where high was before. All right, so we are potentially making those two recursive calls. Now, eventually, we're finally going to end when we don't do this and we don't do this, right? So we stop making recursive calls, which will then allow all the previous recursive calls to unravel. And when all is said and done, the hope is we have a sorted list by over and over and over again, picking a pivot, moving it into position, and going from there. Okay, so don't let me forget to remove an index here. In fact, whatever, just don't let me forget. Let's go test this dude. So we have our quick sort, but I think we wrote a method called sort, correct? That actually makes our initial call here, because that's why we made this guy private. So private, or quick sort method is actually private, which means it's only accessible inside of a list. External to a list, we've provided a public method called sort, this guy right here, that as long as you have something greater than a one list, it goes ahead and makes the appropriate initial call to quick sort. That makes sense? All right, so let's go out to driver. So let's, and we're dealing with strings here, even though you cheated and dealt with integers. Yeah, I remember that. By the way, I am almost caught up with my grading. I expect everything to be since I don't teach tonight. Well, I mean, I'm going out with my wife, but there's several hours in there that I expect to be able to get fully caught up. Oh, Professor Locklear. Mr. Gonzalez has asked me to deliver this to you.
Oh. I'm scared now. At least there's a lot of witnesses here. Okay. Oh, wow. Why, thank you.
I can help you put that tattoo on during Bible study if you'd like.
Maybe not during Bible study.
See, he happens to know who the turtles are, by the way. He knows every one of them. Well, he has kids too, but he knows it for other reasons. All right, so let's add a bunch of alphabet stuff, right? Remind me what we were doing here when we were comparing creating new strings using this syntax versus using this syntax. We were talking about pointers, right? And how string literals don't get reused. Java tries to be intelligent about it, so we need to be careful about those pointers. Okay. In that case, I actually was testing you on that one, and she failed that one. Remember that? See, I always like trying the students that have a lot of experience, just trying to find that one little niche where they don't know. It's entertaining for me. You know, but for everybody, I could do the Teenage Mutant Ninja Turtle thing, and you all fail. And do you know the Turtles?
Well, I know the now.
Well, okay, so if I quizzed you on it, you'll know? Purple guy.
Purple was the smart one.
What's his weapon?
Midterm question.
Huh?
Midterm question.
Midterm question. Like half the midterm is on Teenage Mutant. And then somebody complains, and I argue like, look, it's Teenage Mutant Ninja Turtle theory.
Class, name, weapon, color.
Well, you got to be able to identify via weapon because the original comic book is black and white. I mean, you can't go by their bandana color in that. Noobs. All right, so let's add some out of order stuff to our list here. So we'll do C. A. R. W. B. D. Something like that. And then we'll do lst.display. Let's just make sure everything is copacetic here. All right, there's our unsorted list. then we'll go ahead and we'll say LST dot sort and then LST dot display. Run this dude again. Ruh-roh. So we are walking off the end of our array somewhere. So it's bucket 6 through 5 are our legal buckets. So somewhere we are accessing bucket high in there. So let's look at our code here. Logic would say it might be happening in here. Let's see if that's the... Actually, we can prove that real quick. Let me put a breakpoint in here. Wherever. Let's just see if I get to that that point on the last crash. Actually, that's not gonna... Actually, it might help me. That'll tell me whether the logic's off right from the get-go. So we'll run this guy in the debugger. All right, well, so it's getting there the first time. So let's go ahead and let's throw a breakpoint in here too. Did it actually get put in there? You can do it. Let's stop this. Let's go back to our Java view. Let's put the breakpoint. Oh, maybe didn't like it. I was putting it by comments. All right, so we're getting to the beginning of that the first time through. So let's go ahead and hit play. So this should take us to the next breakpoint. All right, so this guy is. We're still in the for loop. I need to actually elevate this. Oh, whatever. It's a short loop, so we'll just do it. Oh, that was the breakpoint I must have put in, even though it didn't look like a... So is that off now? Okay. So it does look like it's in here, this bottom part. So let's look at our logic there. Even though things didn't seem to be going well with the breakpoints, it worked out okay, I think. All right, so right here is where we're trying to access bucket 6. Let's look at our logic here. So we've already bubbled pivot towards the front. Now we are, let's look at the nature of our original call here. And then a not sort. So the very first time through, we'll bubble D towards the front. So D should end up, oh, actually right where it's at, right? Because it's not going to do that initial swap. All right, because B is less than it. So this is kind of a worst case scenario anyways. All right, so that guy's not bubbled at all. But we've gotten past this initial call, which we saw. You know, we got to that first breakpoint. So now we're going to go from low, which is 0, to pivot, which is bucket, well, pivot's going to be bucket 5 in this case, the last legal bucket. Is that what we put in for? Yeah, we put in high. Did we choose length -1? Yep, so it'd be bucket 5 for pivot. So this is less than bucket 4 because we know that the guy immediately to the left of pivot isn't a problem, right? All right, so if data dot compared to pivot, so that means the first guy we're looking at here, is that this one? No. Is it? Oh, here we go. So should a W come after a D? It should. Okay, and this is where our bug is. So a W should not come after a D. Therefore, well, the W should come after a D. So since this is true, it'll be greater than 0. We're going to go ahead and we preserve the W. Then we shift everything down. So we're going to start with bucket I, which is low. And let's see, J is less than pivot. All right, so this is going to take bucket 0. This guy right here is preserving the very first bucket. It's preserving that C. This is interesting. Because for us, this is the very first time through, right? Oh, no, it's not. It's not. For us, I is ultimately going to get to, should a C come after a D? No. Should an A come after a D? No. Should an R come after a D? Yes. So right now, I is 0, 1, 2. So I is currently equal to 2. So we haven't gotten to the W yet. We're actually starting from the beginning and moving towards the end. So we're sitting at this R. So we go ahead and we preserve that R inside of temp. So temp is currently equal to R. Then we go from this bucket. So J is now pointing to this exact same place. We keep going as long as we're less than or equal to pivot, where pivot is this guy right here, the last legal bucket. And we say J++ each time through. And what we do is we replace this value that we've already preserved with the guy right after it, the W. So now the W shifts up to here. Then we increment. So now we still have a W here, so we replace the W with the B. Then we increment. We replace the B with the D. Then we increment. And we're going up to less than or equal to pivot. And this is where we run into our problem. We are trying to access bucket 6 when there isn't a bucket 6. So in this particular case, since pivot happens to still be the very last bucket, this movement here needs to conditionally occur, right? Okay, it needs to conditionally occur. So we can write a little if statement around that guy. As I mean, we could probably come up with some nicer logic if we want, but you know, we could write an if statement that makes sure that J is not equal to high. Does that make sense? So if J is not equal to high, then we'll go ahead and allow the swap. Otherwise, we just hit that special case where pivot happens to still be at the end. We can go ahead and do the swap. I think the rest of the stuff should be fine. So we just won't do that last swap here. So J is currently sitting here. We swapped it. Then we get to the D. We're not going to swap this guy with the guy after it because that's beyond high. So then we're going to, so this D has already been moved down from the previous loop through. So our current list looks like this. It looks like W, B, D, D. That's what it currently looks like. And pivot is pointing to that D. Okay? So then what do? We replace that D with temp, which was our original R, the guy we preserved before. So then this guy becomes R, so now that's after that dude. And then we decrement pivot because indeed pivot did move one down. Go ahead.
For your line 26, could you just explain exactly like how it's comparing the two since they're strings?
Yeah, so the compare to function, let's actually just put this on the slide so we can say exactly what this guy does. This guy returns a value less than 0 if the calling string should come before. That's interesting that it's not like wrapping. I guess we'll see what happens in a second. Should come before the string parameter. So calling string would be, let's do CS compared to param. So if we say, if CS should come before param, then this guy will return a value of less than 0 because this guy comes before this guy. It'll return a value equal to 0 if CS is the same as param. It'll return a value of greater than 0 if CS should come after param. Now, all of these, this comparison, is actually doing something called lexicographic. No, that's not the right word. Lexicographic. Is it I? Is it an O maybe?
I think the first way you had it was correct. It's
Oh.
LEXI.
Really?
Oh, graphic.
Yeah. LEX
ICO.
ICO.
Generalization of the way the alphabetical order of words is based.
Really? That's how you spell that? Lexicographic. No, well, that's not how I've ever said it. So, but I also learned most of my vocabulary from Mr. Gonzalez. So, yeah. So what this is doing is it's not necessarily perfect alphabetic because it's also going to take into consideration things like question marks and stuff like that as part of the Unicode character set. But for our purposes, it effectively is doing alphabetic comparison. All right, it's at the final baseline. It's not exactly what we would call alphabetic, where we only consider the alphabet. It's doing things beyond that. All right, so this is kind of our way of saying, should this string come before this string, vice versa. So we look at the result of that, which is a numeric result, and most implementations have it return a -1 for this, a 0 for this, or a +1 for this. But the historical precedence for this is that it's less than 0, equal to 0, or greater than 0. That's actually the same historical precedence there is for Boolean. Typically, you go back to the early C language where Booleans were actually implemented as ints, where it was 0 or 1, true or false. Non-zero was considered false, even though it was usually implemented as a 1. But anything other than 0, so the appropriate way to check it was check it against being equivalent to 0 as opposed to being equal to 1. Yeah, so it's falls into a similar category as I've mentioned to you before. Don't rely on default values. You know, you create an array. In Java, arrays do get filled with a bunch of zeros. Don't rely on it. If you want an array to be filled with zeros, fill it with zeros. It's not going to take up that much time. It's something you're only doing once. And then you can 100% trust that that guy is filled with zeros and your code is future-proof, let's say, because you don't know, and this has happened before in older languages like the GCC compiler started giving, for the C programming language, actually it might have been G++ for the C++ programming language when this happened. Prior to that, it did not put in default values for like an integer. If you just said int A, int A was pointing to some memory address, and the value you would get from that guy is whatever used to be there. Then it started giving it an initialization value for correctness. Well, if your old code, sometimes people would use the old data that was at memory addresses for random data. They would just say, oh, well, memory is, let's say it's mostly random, so I'm just going to let the system find the memory address for me at random, and whatever value is currently there, that's my random number. That's my random value. Well, all of a sudden you started getting zeros for everything. So, that kind of breaks your logic. So, the idea is that if you want something to hold a value, put a value there. Don't rely on a default value. All right, does that make sense how this compare to works? All right, so this guy should prevent us from doing a comparison off the end of the list here in our special case. Let's see if we pass the test now, or if we bump into a new bug. ABC, that does not look sorted to me. Everything to the left, well, it starts off doing pretty good. All right, well, let's follow our algorithm then on our actual data and see where we're going south. So this is my original stuff right there, right? Car WBD. Okay, I'll move these guys down here. First thing we do is we make our call from low to high. So this should be good.
I think it was BD.
BD. Is it BD? Okay, thank you. So first thing our code says to do here in sort, as long as the length of our data is greater than 1, which ours is, call low is 0, high is length minus 1. So low is 0, high is length minus 1, which will be 5. And then we set pivot equal to 5. We're just keeping track of the value that's in pivot. Okay, or the position of pivot rather. So that's 5. That's the first thing we do right up here. We set pivot equal to high. Now, as long as pivot is greater than low, so not at the beginning of the list, and we should swap it with the guy before it, that is, the calling string, pivot, should come before the parameter. So as long as pivot should come before pivot minus 1. So here's pivot. Should a D come before a B? It should not. So we fail the very first time, which is fine. So we have bubbled pivot as far forward as we possibly can. So we're past that. Now we come into this loop. I equals low, I is less than pivot minus 1, I plus plus. So let's give ourselves an I here. Get rid of that guy. And we start I off at low. So in this case, low is 0. Is the current value of I, which is 0, is that less than pivot minus 1? It is. Pivot minus 1 is going to be 4. 5 minus 1 is 4. So that's true. So we come in here, we ask, is the string at bucket I, should it come after the string at bucket pivot? Should a C come after a D? Should not, right? So we're not doing a swap there. So we fail this. don't do anything inside the if statement, loop back up, I is now 1. Should an A come after a D? Nope, I is now 2. Should an R come after a D? Yes. So let's switch our I up there. All right, so I is currently 2. We get into the if statement because the current value at 2, which is R, should come after a D. I'm going to go ahead and grab this because we're about to create another variable called J. All right, so now we are inside of this logic right here. The goal being move the current value after the end of our after pivot, well, into position pivot and shift everything else down. That's what we're ultimately doing here. So we're going to say temp is equal to the current value we're trying to swap out, which is this R. So let's get our temp here. And temp is going to be equal to R. That's the ultimate guy that we want to move into bucket pivot at the end. But in order to replace this guy with this guy, I need to move all this stuff down into this position to free up this last space. Okay? So now we get into this for loop. So J is going to start off at I, which is currently 2. So J is the same as I. Keep going as long as J is less than or equal to pivot. Pivot is 5. Actually, pivot is 5 right now, so less than or equal to pivot will be 5. J plus plus. We actually could. This might actually be our issue right here, but let's follow it and see if we bump into it. This might need to be less than. So we asked the question is long as J is not equal to high, right now they're not equal to each other. J is 2, high is 5, they're not equal to each other. So we're going to go ahead and we're going to set bucket J equal to bucket J plus 1. So we will, bucket J is 2, so we will replace that R with that W. We have preserved the R though, we haven't lost it. All right, then we increment J, so J is now 3. Is 3 less than or equal to, it's less than or equal to pivot, right? Yep. Is 3 less or equal to 5? It is. So we ask the question, should, are we allowed to swap this guy and this guy? Are they different values? Yes. So we'll go ahead and move the B here. We'll increment the J. J is now here. Are we allowed to swap these two? Yes, so we'll move the D here. Increment the J. Is J less than or equal to pivot? It is. So this is why we had to put in that special case a few minutes ago, although I think we could have probably avoided this by doing less than in that for loop. But our logic hasn't broken yet. So we're not going to actually do any swap here because there's nothing left to do. So we do fail. That guy right there is J not equal to high. Current value of J is 5. Current value of high is 5. We won't do anything there, so we're still fine. Then we fall out of this for loop and we replace this at bucket data with pivot. Or I'm sorry, this data at bucket pivot with temp. Pivot is at 5 right here. Temp is R, so we put that R right there, moving the value after our current value of pivot. Then we decrement pivot because our pivot has moved. So pivot is now a 4. Our old pivot has moved to that position because we had to put an extra dude after this. Okay, so we fall out of this inner loop. So this guy is now done. We spin back up and we move ourselves, well actually all of this is done. We spin back up, we move I to its next value, so I plus plus. I is now 3. Is 3 less than pivot minus 1? Oh, this is our problem. Pivot is moving there. So we didn't fully go through our loop here because pivot kept moving. So we probably need to... No, actually, maybe that's okay. Pivot just went from here to here. And we know everything that's before that is where it used to be, with the exception that if pivot moved, it's because the thing we put after that needed to go after that. So I don't know that this is broken yet. So pivot did move. We're going to ask the question, is the current value of I less than pivot minus 1? I is 3. Pivot is currently 4. 4 minus 1 is 3. Where's I? I is... How did I get to 3? Oh, we skipped this. When we bubbled it down, we actually needed to do that iteration again. We're sitting right here and we abandoned this W. We never actually dealt with the W and making it go after the thing after it because we went ahead and let I increase by 1 when everything else decremented by 1. So when we moved all this stuff, by having to do that swap, we then, in the current way we're doing this, need to artificially decrement I so that this is a wash. I minus minus I plus plus says redo the last I because the last I is actually checking a new value now. That make sense? So with that in mind, I is still 2. So that means we're still looking at this guy here. Is 2 less than 4 minus 1? It is. So we get inside of this for loop. We ask the question, is the current value at I, when compared to the current value of pivot, should it come after that? Should a W come after a D? It should. So we need to move that guy. So we preserve the W inside of temp. There's our W. We shift everything down. So this is going to be B, D, R. Then we'll overwrite this last guy with the W. Pivot then becomes 1 smaller than it used to be. I becomes 1 smaller than it used to be, then increases. Because we do I minus minus, then we do I plus plus. So pivot remains the same. We spin back up and we say, so our current value of pivot is 3. So we decremented it. I is now 2. Is 2 less than 3 minus 1? It's not. So our current pivot is D. Is everything before D less than or equal to D and everything after D greater than D? Looks correct now in terms of moving that guy where he needed to move. So now we can say that D is in his final place. That was what we were not able to say before because we were actually not doing all our comparisons because we were having one thing move this way and another thing move this way and we were skipping a bucket. Does that make sense? So then we call the same logic on everything before, the same logic on everything after. All right, so let's see if this guy does what he's supposed to do now. Now our stuff looks properly sorted. That makes sense. Now, we probably could have, I think we could avoid having this if statement in here if we say less than here. I think that'll cover us in all bases because less than pivot says we don't need to do the stuff after it. So I think if we move this to a less than, and then do this, we get the equivalent logic without having to ask the extra question every single time through. So technically this would be a little bit quicker, because before we had wrapped this guy in a question, and that's kind of what big O notation, I like to think about big O notation is effectively that. How many questions do we have to ask to solve this problem? Maybe a little bit more complicated than that, but I think if you were to abstract it, I think that's an accurate way of describing it. The more questions you have to ask, the slower the algorithm. Kind of makes sense? So we can certainly say that if every single time through this loop we were asking an extra question that really could have been solved by making a small modification to that Boolean expression, we could speed things up doing it the way we just did it. Now, because we started at that last thing, and we're doing, I mean, this should probably look a little weird to us. The fact that you're incrementing I here and you're decrementing I here, you could maybe do a conditional increment, but this might lead you to say, well, maybe I should do this guy as a while loop or something like that, and only conditionally change I, but this isn't hurting anything. And this isn't really a question. It's a quick little math operation. Technically, it does take time, but in the big scheme of things, a relatively small amount of time. Make some sense? All right, so I think this is at least a reasonable implementation of quicksort. I guess there's potential in here that we might still have some sort of weird special case bug, but since I feel pretty good about it, since we're making sure that we only pass it to it if we have a length greater than 1. So I don't think we have to worry too much about those special cases of 1 lists and 0 lists and that kind of stuff. Okay, so let's go ahead then and let's write, what was it? Remove it index, okay. So this is going to be public void remove at index, and this guy's going to take in an int index as a parameter. Okay. Oh, I wrote it somewhere. That's right. I had this thing. I had pre-written it, right? It's down here somewhere. There we go. So this returns as well as remove. So this guy ultimately returns the dude we're removing, but also removes it from the A list in this case. Okay. So what we need to do is I think we had maybe the class right before I assigned this, we had talked about the exceptions and runtime errors and those guys. So we potentially could have do a runtime exception here where if you try to remove something at index that doesn't actually exist, we could scream at you and that kind of stuff. So we can ask some questions in here. Just get rid of that for a second. We can say something like if index is less than 0 or index is greater than this dot data dot length minus 1. So if it's outside of the range of what's legal, but this is if it's greater than it.
Oh, okay.
Yeah, if the thing you're trying to remove is beyond the end of the list. I'm trying to think, what would this do for a 0 list? Index is greater than, 0 list would have a length of -1, so that would work. Yep. So this will handle our illegal index positions. If you ask for something before the beginning or after the end, we're going to scream at you. All right. So we can do new runtime. Was it just runtime exception? bad index. And then we're going to throw that guy. Oh, it's yelling about I haven't returned a value. So we're okay so far. All right, so this is our runtime exception. This is the special version of our exception that says, hey, I'm pretty lazy. I want to scream at the end user, but I don't want to have to deal with exceptions because they shouldn't have given me a bad value. So you're just haha. So that's the difference between a runtime exception and a normal exception, is we don't have to specify that this dude throws something. He just gives us an error. Similar to integer.parseInt. So if you use integer.parseInt and you try to squeeze the integer value out of the word hello, that guy gives you a runtime exception. You don't have to wrap that in a try catch or anything. It just will scream at you and say, stop being stupid. Okay, so now we'll have our else. So if we're in this else, that we then know that index is a legit position inside of our array list or a list, whatever we called it, a list. So we need to go ahead and ultimately grab the guy first, because that's going to be the dude we're going to finally return, right? So we'll say string val to return is going to be equal to this dot data at bucket index. And then down here at the bottom, we can go ahead and say return val to return. All right, because that's the string we're ultimately going to return. But here in the middle, we need to shrink our A list and get rid of bucket index. All right, so we're going to need a new data array, because remember the whole point of A list is to kind of, really exaggerate the idea of a destructive array, and that, under the hood we can have the guy do everything we ever want it to do, as long as we just don't care what it's doing to memory. But it's not our problem, right? We got plenty of memory, so we could use our A list all year round for most problems, and probably we would never run into problems until we finally did. When we had something that was storing too much data, where all of a sudden, even with your 16 gigs of RAM, it started saying, whoa, you are doing some stuff that you should not be doing, using too much memory. Okay, so we need something that's going to be one smaller than it used to be. So we'll say string array temp is equal to a new string array of size data.length -1, so one smaller than it used to be. We're going to go ahead and grab everything before bucket index in our array and fill it into the equivalent buckets in temp, right? So for int I is equal to 0, I is less than index I plus plus. And remember, for loops are pre-check loops, so there's no guarantee that this is going to actually remove anything. Okay, we might go through this loop 0 times. That index happens to be at bucket 0. That's the guy we're removing. Because if index was bucket 0, we start I at 0. Is 0 less than 0? It's not. So we won't even go through this loop one time. One of the advantages of a pre-check loop in this case. And we'll go ahead and say temp at bucket I is equal to this dot data at bucket I. All right, so we went ahead and filled up temp with everything prior to index. Now we need to go through and get everything after index. So for int I is equal to index plus 1, I is less than this dot data dot length, I plus plus. So everything after index, we are now putting into bucket, we can say I minus 1 in our original list. So we can do that, or we could have also just had a counter. If I'm writing this to try to decrease the amount of the error rate of this, I would probably have written something called int pause and start that off at 0. And I would always be filling temp at bucket pause. And then I would do something like pause plus plus. So then rather than having to do weird math with I here, I'm just going to continue on and keep filling up temp from bucket pause, because that's the next bucket I want to fill in temp. So I'll say temp at bucket pause is equal to this dot data at bucket I. And then pause plus plus. So this gets everything before index. This gets everything after index. We know that temp is one smaller than data.length was, and pause takes us on our voyage through temp. I takes us on a voyage through data, omitting bucket index. At the very end, we'll say this dot data is equal to temp. So data now points to the new array we've created in memory. And then ultimately we'll return the value that we wanted to return. So let's go ahead and write this. Actually, let's just to simplify the output here. Let's get rid of our sort. We'll display, then we'll say lst dot remove at index. Let's just do 2. That should get rid of the R. lst dot display. So there's with the R, there's without the R. Let's test it for first and last buckets. So there's 0. That should remove the C. There's with the C, there's without the C. And then last bucket is going to be, 5? So it should get rid of the D. There's with the D. There's without the D. And then we'll go ahead and see our runtime issue. So we'll say 6. There's our bad index runtime exception. And then we'll say, pick your favorite negative number. There's our bad index exception. All right, so questions about that remove it index? And what I'll go ahead is I'll just copy all this code and I'll paste it into Slack real quick just so you have a copy of what we wrote. Oh, I have Slack on this computer, don't I? Yeah. And then is that everything we're supposed to do? Now we can start talking about linked lists. Do. 300 code snippet. Quick sort and remove at index plus plus. I don't know what else was in there that we hadn't previously posted, but okay. So since you've read about it, I'll go relatively quickly on linked lists. All right, so linked lists, they represent kind of our first traditional data structure that we usually discuss in a data structures course. Data structures typically come in kind of 3 different formats, and the first of those 3 formats are linearly linked data structures. And linked lists are one of those. The 3 popular ones of those are linked list, stacks, and queues. Okay. That's not all of them that exist, but that's because you got things like vectors and stuff like that also are this type of thing. But linked list is kind of our primitive version of this. So they're the jack of all trades. And then stacks are special purpose linked lists, and queues are special purpose linked lists, or linked lists that act a specific way. All right. So we're going to focus on linked lists first, and then we'll get into stacks and queues. And your book may have already started mentioning stacks and queues, did it?
No, but it shows that they're going to be talking about later in the chapter.
Okay. But linked lists is what we're interested in initially. And when I say linked lists are generic, so they come in a couple of forms. We have singly linked lists. We have doubly linked lists. We're going to start off looking at singly linked lists. And when we say, and I'll talk about that here in a second, when we say singly linked lists, or even linked lists in general, when we compare them to arrays, we're going to say linked lists are relatively slow but very memory efficient. Arrays are relatively fast but very memory inefficient. Okay. Oh, wait. Do we have like... We'll use that guy. So they're bad. Well, not bad. They're fast, but memory inefficient. And that's what we've been drilling up to this point. So our whole A-list thing, while perfectly, I got a fire guy, while perfectly acceptable, we can all accept the fact that we did a lot of destroying and recreating under the hood, right? Not our problem, that's the computer's problem, and most of the time, not going to hurt anything. What do we care about the memory? When we're done with our program, we'll reclaim it and move on with life. Okay? But every now and then you're going to be solving a problem where memory efficiency might come into play. If you're solving some big scientific type thing, is doing a lot of data storage, a lot of number crunching, you're implementing a database where it needs to work on an arbitrary amount of information, your 16 gigabytes might quickly become less huge. Okay, so these things then make a difference. Now, if we talk about problems, so you can say why arrays are memory inefficient. We can point to we've seen the whole thing that if we want to change the size, we destroy it and create a new one, all that stuff. But it ultimately comes down to one kind of fact, one thing about how arrays actually work. And that's this idea of contiguous memory. So arrays require memory in a row. That's good enough. That's what contiguous memory is. So that one point about arrays, the fact that they require contiguous memory, it answers both sides of the coin. It's why they're fast. Because with memory in a row, we can calculate the position in memory of an individual bucket. Because we know everything is relatively in the same neighborhood. And when I say they're exactly in the same neighborhood and they're right next to each other. So because we know that about arrays, having them in contiguous memory allows us to calculate bucket 7 and just immediately go there. That's what makes them fast. But having them in a row means that if we want to change the size of it at all, we have to recreate it. Now, some hacks with that. Let's say that you know that, I'll never have to store more than 10,000 things. Maybe you operate off that element where you just say, well, our A list allows you to store up to 10,000 elements. It's probably going to solve most problems, right? I mean, if you don't like 10,000, that's not enough. Pick a bigger number. Pick 100,000. Pick 1,000,000. And some number that you can, write. And it's got to be less than size of int in order to use it as the index for the size of array. Okay. But what some people have historically done to get the speed without having the destructive nature of it is they'll say, look, I'm just going to build the giant mansion. Yeah, it's just me and some cats, So I only need 1 bedroom. I have 30. Maybe I'll get some more cats or something like that. Okay, so we'll build the giant mansion, giving us plenty of room to grow into if we choose to. Downside of that is right off the bat, we're asking our operating system for a whole bunch of memory, right? And that memory is now off limits for anybody else. But 100,000, I mean, so if we, let's just use that as a number. So we have 100,000 integers, let's say as an example. So an integer is 4 bytes. So that's 400,000 bytes. Okay, divide that by 1,024, that's kilobytes. Divide that by 1,024, that's megabytes. Divide that by 1,024, that's gigabytes. Okay, so I have that number. I have 16 gigabytes of memory in my laptop here. If I want to store 100,000 ints, it's going to take up 0.0003. We'll round up. 0.0004 of those gigabytes. Negligible. I'll never miss it, right? Who cares? It's kind of the American way, right? It's like, I read it. Actually, it was in the. Did you see the movie Contact? Jodie Foster. It's like a SETI Search for Aliens thing. Really good movie. Good book too. But the one of the entrepreneur guys in it said something like, the American way. Why build one when you can build 2 at twice the cost? And the thing is since our machines have so much memory in them today, we can make the argument that that's okay. That we're allowed to just use memory haphazardly like that. So that we're not living back in the 70s and 80s where this was a major issue. All right, so we have our contiguous memory. Now, since we only have a minute left, we look at implementation. And I'll have you, because you did read about add front, add end, right? So for implementation, our arrays or our linked lists are going to be implemented. And let's do it as strings right now, since that's what we've been messing with. We're going to have a node class, and a node is going to be a string payload, and it's going to be a node next node. So every node knows about the next node that comes in it. Then you'll have the linked list class, and this guy's going to have a node head where you know about the front of the list. And then we're going to have a method add front and a method add end. And then a method called display. All right, so for your homework for next class, implement the node class that just has 2 attributes. It's going to keep track of the payload, the piece of information that we're storing at that particular bucket in my linked list, as well as the next node in memory, because linked lists are not contiguous. So this node right here, in order to get to the next guy in the list, he needs to have a pointer that leads us to the new place in memory where he lives. And we'll need to make sure we update those pointers when we add stuff to either the front or the end of our linked list. These 2 methods are pretty easy to write, add front and add end. So this would be a good warm-up getting back into programming stuff, I guess. All right, questions about what I'm asking you to do for Thursday? All right, should be pretty straightforward. I'm guessing the book has some sort of simple implementation in it probably, but if you're going to use what's in the book, that's fine. Just make sure you understand what it's doing. All right. All right, I will see. Yeah, prepend, upend. Yeah. All right, I will see everybody on Thursday. Don't forget, today is Faculty, Student, Staff Bible Study. It's at noon. Just go to the cafeteria, sign in, you get free lunch. God and grub, just take your tray down to the terrace room and eat your lunch and have Bible study and blah, blah, blah. I'll be there, so will the rest of the computer science faculty and stuff, so feel free to sit with us.